A kilometre-wide asteroid drifts through the vacuum of space, its surface carved by 4 billion years of cosmic bombardment. The rock carries within its crystalline structure the memory of the early solar system metals forged in dying stars, organic compounds that never quite became life, water ice locked in shadow-cold crevices that have remained undisturbed since the Hadean Eon. It tumbles slowly through the void, one rotation every 6 hours and 14 minutes, revealing faces of stone that have never known warmth beyond the faint touch of distant starlight. Each crater on its surface tells a story of impact, of smaller objects that struck and embedded their own histories into the asteroid's growing mass. Some of these craters hold deposits of rare earth elements, concentrated by the gentle chemistry of slow collisions over geological time. The asteroid's composition reads like a periodic table, written in stone, iron and nickel from the cores of ancient planetesimals, silicon and aluminum from the mantles of worlds that never grew large enough to hold atmospheres, carbon compounds that formed in the cold spaces between stars. The Sun grows larger in the asteroid's predetermined path, no longer a distant star but a sphere of roiling plasma that fills an ever-expanding portion of the cosmic horizon. At this distance, still millions of kilometers away, solar radiation begins to affect the asteroid's delicate equilibrium. Ice sublimes directly from solid to gas without the intermediate step of melting, creating a faint coma of vapor that streams away like the breath of something slowly dying. The asteroid's surface temperature climbs past the melting point of zinc, then lead, then any substance that might have existed in Earth's patient geology. The pressure of solar radiation becomes measurable now, pushing against the asteroid's surface with the force of pure light. Photons carry momentum, and at this proximity to our star, that momentum accumulates into a tangible push that slightly alters the asteroid's trajectory. This radiation pressure, so gentle that it would barely move a feather on Earth, becomes significant in the vacuum of space where no air resistance exists to mask its effects. The asteroid begins to accelerate, pulled by the Sun's immense gravitational field and pushed by the star's own light. Spectrographic analysis, were any spacecraft present to perform it, would reveal the asteroid's surface composition changing in real time. Volatile compounds, sulfur, phosphorus, organic molecules vaporize first, creating a thin atmosphere around the rocky mass that immediately streams away in the solar wind. This temporary envelope glows faintly in ultraviolet light, visible only to instruments sensitive enough to detect such subtle emissions against the overwhelming brightness of the approaching sun. The photosphere finally approaches that deceptively calm-looking surface that burns at 5,778 Kelvin, hot enough to vaporize any known material yet somehow appearing almost solid when viewed through the filtered light of solar telescopes. This outermost visible layer of the Sun extends barely 500 kilometers deep, thinner proportionally than an apple's skin. Yet it contains more energy than humanity has ever produced, consumed, or even imagined. The asteroid crosses this boundary without ceremony, like a grain of sand falling into an ocean of nuclear fire. Plasma immediately engulfs the rocky mass, and the physics of the encounter becomes almost impossibly violent. Here, in this realm of superheated gas, atoms move so frantically that electrons tear away from their nuclei, creating a conducting soup of charged particles that responds to magnetic fields with liquid grace. The asteroid's surface begins to melt, then vaporize, then ionize into its component elements in a cascade of phase transitions that happens faster than human perception could follow. The granulation patterns of the photosphere convection cells, the size of small countries rising and falling in precise 5-minute cycles, briefly distort around the asteroid's presence. These cellular structures, driven by the heat engine of the Sun's interior, carry energy upward from depths where nuclear fusion transforms mass into light. The asteroid's intrusion creates temporary asymmetries in these patterns, ripples in the otherwise orderly process of energy transport that propagates outward at the speed of sound through plasma. Silicon dioxide, the primary component of the asteroid's rocky matrix, dissociates into its constituent atoms at these temperatures. The silicon nuclei, stripped of all their electrons, join the plasma soup while the oxygen atoms contribute to the complex chemistry of stellar atmospheres. Iron and nickel, the asteroid's metallic core materials, ionize completely, their electrons moving independently through the plasma, while their nuclei become part of the Sun's vast reservoir of heavy elements. Scientists have calculated through sophisticated computer models that an object this size would survive perhaps 30 to 45 seconds in the photosphere before achieving complete dissolution. Only took the Sun 4.5 billion years to build such an efficient furnace. The irony rests quietly in the mathematical equations this asteroid, born from the same stellar collapse that created our Sun, returns now to the nuclear fire that originally forged its constituent atoms in the death throes of previous generations of stars. The temperature differential between the asteroid's relatively cool core and the surrounding plasma creates shock waves that propagate outward through the photosphere at supersonic speeds. These disturbances travel like ripples in a pond of light, carrying the asteroid's final signature toward the Sun's edge. The waves weaken with distance, their energy absorbed by the constant turbulence of solar convection, but sensitive instruments could potentially detect them as minute oscillations in the Sun's surface brightness. Magnetohydrodynamic effects become significant as the asteroid's metallic components interact with the Sun's magnetic field. The field lines, normally invisible rivers of magnetic force that arch high above the photosphere, respond to the sudden introduction of conducting material by reconnecting and reforming in complex patterns. These magnetic reconnection events release stored energy in brief, intense flashes that contribute to the overall dynamics of the solar atmosphere. One profound mystery persists in the plasma physics of this encounter, the exact mechanisms by which the Sun's magnetic field lines respond to such sudden introductions of foreign conducting material remain incompletely understood. Theoretical models suggest cascading reconnection events, where field lines snap and reform in fractal patterns, releasing stored magnetic energy in bursts that contribute to the heating of the corona above. The asteroid becomes a temporary catalyst for phenomena that solar physicists continue to study through computer simulations and spacecraft observations. Time dilates strangely in this environment, where the normal rules of matter and energy bend toward their extreme limits. The photons created by the asteroid's dissolution, light born from the conversion of matter in the Sun's nuclear furnace, now mixed with light from the asteroid's complete destruction, will take thousands of years to random walk their way outward through the Sun's dense interior. These photons will scatter countless times off free electrons and nuclei, each scattering event changing their direction randomly, before finally escaping as visible light that will someday warm distant worlds. The photosphere continues its ancient rhythm, essentially unperturbed by this brief addition of foreign matter that represents less than a billionth of the Sun's total mass. Convection cells rise and fall with metronomic precision. Magnetic field lines twist and reform according to the dictates of plasma physics. and the Sun's surface temperature holds steady at exactly the temperature required to sustain the delicate atmospheric chemistry that makes life possible on a small blue planet orbiting 93 million miles away. The asteroid's remnants pass beyond the photosphere into the chromosphere, that thin intermediate layer where the Sun's atmosphere begins its transformation from merely hot to impossibly energetic. Here, in a region extending barely 2,000 kilometers above the visible surface, temperatures paradoxically increase with altitude, climbing from the photosphere's 578 Kelvin to nearly 20,000 Kelvin at the chromosphere's upper boundary. This temperature inversion defies intuition. Moving away from a heat source should mean cooling, not heating yet. The chromosphere burns hotter than the surface below. What remains of the kilometer-wide object now exists as a cloud of ionized atoms, each nucleus stripped of its electron shell and moving independently through the increasingly tenuous solar atmosphere. The asteroid's silicon atoms, once locked in crystalline matrices that formed over millions of years in the asteroid belt's patient cold, now race through space at velocities that would carry them from New York to Los Angeles in under a second. Their kinetic energy alone exceeds the binding energy that once held continents together on long-vanished worlds. Hydrogen dominates this region of the Sun's atmosphere, comprising roughly 73% of the chromosphere's mass. The hydrogen atoms here exist in a state of constant excitation, their single electrons jumping between energy levels as they absorb and emit photons in the deep red wavelength of 656.3 nanometers. This specific color, the alpha line of the hydrogen Balmer series, paints the chromosphere in shades of crimson that become visible only during solar eclipses. When the moon's shadow blocks the photosphere's overwhelming brightness, the asteroid's carbon atoms, once part of organic compounds that might have seeded life on some distant world, now contribute to the chromosphere's complex emission spectrum. Carbon ions, missing several electrons, emit characteristic wavelengths of ultraviolet light that spacecraft instruments can detect and measure. These spectral lines serve as fingerprints, allowing solar physicists to trace the asteroid's dispersal through the Sun's atmosphere with remarkable precision. Each element announces its presence through its unique pattern of emitted light. Spicules rise from the chromosphere's lower boundary like grass blades made of plasma, each structure reaching heights of several thousand kilometers before falling back toward the Sun's surface. These jets of hot gas, discovered through high-resolution solar telescopes, erupt at velocities approaching 30 kilometers per second, fast enough to escape Earth's gravity entirely. The asteroid's atoms become entrained in these spicular flows, carried upward on currents of magnetized plasma that follow the invisible architecture of magnetic field lines. The chromosphere's density measures approximately 1/10,000th that of Earth's atmosphere at sea level, so tenuous that it would qualify as an excellent vacuum by terrestrial standards. Yet this near emptiness teems with activity invisible to human senses. Acoustic waves generated in the photosphere's convection zone propagate upward through the chromosphere, their energy gradually converting from sound into magnetic oscillations that will eventually heat the corona above. The asteroid's dissolution adds brief perturbations to these wave patterns, like dropping a stone into a pond of light. Magnetic field lines thread through the chromosphere in complex geometries that change constantly as the Sun's internal dynamo shifts and evolves. These field lines act as guides for charged particles, channeling the flow of ionized gas along invisible highways that arch high above the solar surface. The asteroid's metallic components, iron, nickel, cobalt, become caught in these magnetic streams, their motion constrained to follow the field line's curved path through three-dimensional space. The chromosphere's temperature structure presents one of solar physics' enduring puzzles. Heat should dissipate with distance from its source, yet this atmospheric layer grows hotter with altitude, reaching temperatures that approach those found in the cores of other stars. Current theories propose that magnetic waves, generated by the turbulent motion of the photosphere below, carry energy upward and deposit it as heat through a process called magnetic reconnection. The asteroid's passage briefly disrupts these energy transport mechanisms in ways that remain difficult to model accurately. Helium becomes significant in the chromosphere's composition, making up approximately 25% of the atmospheric mass. This helium exists primarily in its neutral state, though increasing numbers of helium atoms lose one electron to become singly ionized as temperatures climb toward the transition region above. The asteroid's original helium content captured from the solar nebula during the early solar system's formation merges with the Sun's own helium inventory, adding an infinitesimal fraction to the reservoir of fusion products created in the stellar core. Chromospheric heating mechanisms operate through processes that remain partially mysterious to contemporary astrophysics. Magnetohydrodynamic waves, generated by the convective motions of the photosphere, propagate upward and steepen into shock waves that dissipate their energy as heat. Magnetic flux tubes, twisted by the differential rotation of the Sun's surface, store energy that releases suddenly when field lines reconnect and snap back to lower energy configurations. The asteroid's atoms become witnesses to these fundamental processes, their emission spectra recording the signatures of heating events too brief for human instruments to capture directly. Time scales in the chromosphere span from seconds to hours, depending on the phenomenon under observation. Spicules form and dissipate in minutes, while larger magnetic structures persist for hours or days. The asteroid's dispersal occurs on intermediate timescales, its constituent atoms spread through volumes of space larger than Earth within the first few minutes after dissolution. Yet the complete mixing with the chromospheric medium requires several hours of diffusion and magnetic transport. The transition region looms above, where temperatures will jump from the chromosphere's 20,000 Kelvin to the corona's 2 million Kelvin, across a boundary layer barely 100 kilometers thick. This represents one of the steepest temperature gradients known in nature, comparable to moving from Antarctic ice to molten steel across the width of a single city. The asteroid's atoms prepare for this transition by losing more electrons, their ionization states increasing as thermal energy strips away the remaining electron shells. Energy balance in the chromosphere depends on the delicate equilibrium between heating and cooling processes. Radiative cooling, primarily through hydrogen and helium emission lines, removes energy from the system while magnetic heating mechanisms add energy back. The asteroid's contribution to this energy budget remains negligible on a global scale, yet locally, its presence creates brief imbalances that propagate outward as waves and disturbances in the plasma medium. The chromosphere serves as a laboratory for plasma physics under conditions impossible to replicate on Earth. Magnetic field strengths here reach several thousand Gauss thousands of times stronger than our planet's magnetic field, while particle densities span ranges from the best terrestrial vacuums to the density of water vapor. The asteroid's atoms experience physics at these extremes, their behavior governed by equations that describe matter in states of ionization and temperature that exist nowhere else in the solar system. Red light from hydrogen alpha emissions creates the chromosphere's distinctive color signature, visible to specialized solar telescopes equipped with narrow-band filters. This deep crimson glow, reminiscent of heated iron in a blacksmith's forge, results from electrons dropping from the third to the second energy level in hydrogen atoms. The asteroid's hydrogen content, originally incorporated as water ice and hydrated minerals, now contributes to this cosmic neon sign that announces the presence of the Sun's middle atmosphere to any observer equipped with the proper instruments. The asteroid's dispersed atoms enter the corona, crossing the transition region, where temperatures leap from 20,000 Kelvin to 2 million Kelvin across a boundary thinner than the distance between neighbouring buildings. This temperature jump occurs so abruptly that it defies conventional understanding of how heat should behave. In terrestrial experience, temperature gradients smooth out over distance. A hot stove cools gradually as you move away from it. Yet here, in the Sun's outermost atmosphere, the normal rules of thermodynamics bend around magnetic field lines that store and release energy through mechanisms still being discovered by solar physicists. At 2 million Kelvin, the corona exists in a state of matter so extreme that every atom becomes completely ionized. Electrons, torn from their nuclei by the violence of thermal motion, move independently through space at average velocities exceeding 1,000 kilometers per second. The asteroid's iron atoms, once part of metallic grains that condensed in the cooling disk around the young Sun, now exist as bare nuclei carrying positive charges of 26-1 for each missing electron. These iron ions race through the coronal medium with kinetic energies equivalent to particle accelerator beams. The corona's density measures 1/trillionth that of Earth's atmosphere, making it a vacuum superior to anything achievable in terrestrial laboratories. Yet this near-perfect emptiness glows with X-ray emissions visible to space-based telescopes, its light generated by electrons spiraling around magnetic field lines in a process called synchrotron radiation. The asteroid's contribution to this emission appears as a brief brightening in the X-ray spectrum, detectable by instruments sensitive enough to measure individual photons against the corona's steady background glow. Magnetic field lines dominate the corona's architecture, creating structures that arch hundreds of thousands of kilometers above the Sun's surface. These field lines, invisible to the naked eye but revealed through their effects on charged particles, form loops and streamers that follow the magnetic topology generated by the Sun's internal dynamo. The asteroid's ionized atoms become trapped along these magnetic highways, their motion constrained to follow the curved geometry of field lines that connect different regions of the solar surface. Coronal loops, some large enough to encompass several Earths, pulse with 11-minute oscillations that reflect the acoustic modes of the Sun's interior. These standing wave patterns, generated by pressure waves bouncing between the photosphere and the base of the convection zone, propagate upward and modulate the coronal plasma density with mathematical precision. The asteroid's atoms ride these acoustic waves like surfers on invisible swells of sound that travel through plasma at velocities approaching the local speed of light. The solar wind begins its acceleration in the lower corona, starting as a gentle breeze of charged particles and eventually reaching supersonic velocities that carry solar material beyond the edge of the solar system. Protons and electrons, heated to temperatures where their thermal velocities exceed the Sun's escape velocity, stream outward along open magnetic field lines that extend into interplanetary space. The asteroid's hydrogen nuclei join this cosmic river, their destiny now tied to the solar wind's journey toward the heliopause and beyond. Coronal heating mechanisms operate through processes so complex that they require supercomputer simulations to model accurately. Magnetic reconnection events, where oppositely directed field lines approach each other and suddenly snap together, release stored magnetic energy as heat and particle acceleration. These reconnection sites appear throughout the corona as bright points in X-ray images, each one a miniature laboratory where the fundamental physics of plasma behavior plays out on scales ranging from meters to thousands of kilometers. The asteroid's heavier elements, silicon, magnesium, aluminum, become highly charged ions that emit characteristic X-ray lines when their remaining electrons transition between energy levels. These emission lines serve as diagnostic tools for coronal physicists, revealing temperature, density, and magnetic field strength through spectroscopic analysis. The asteroid's brief passage creates temporary enhancements in these spectral signatures, like adding a few drops of food coloring to a vast ocean of plasma. Wave heating represents another candidate mechanism for coronal energy deposition. Alphen waves, magnetohydrodynamic oscillations that travel along magnetic field lines, carry energy from the photosphere's turbulent convection into the corona's tenuous medium. These waves, named after Swedish physicist Hannes Alfvén, propagate at velocities determined by the magnetic field strength and plasma density. As they steepen into shock waves, their kinetic energy converts to thermal energy, heating the coronal plasma to its extreme temperatures. Time scales in the corona span from milliseconds to years, reflecting the diverse range of physical processes operating in this exotic environment. Magnetic reconnection events occur in seconds, while coronal mass ejections develop over hours, and large-scale magnetic structures evolve over the 11-year solar cycle. The asteroid's atoms experience all these timescales simultaneously, their individual trajectories determined by rapid magnetic fluctuations, while their collective behavior follows the slower evolution of large-scale coronal structures. The corona extends far beyond the visible disk of the Sun, stretching millions of kilometers into space as streamers and plumes that follow magnetic field lines. During total solar eclipses, when the Moon blocks the photosphere's overwhelming brightness, the corona becomes visible as a silvery nimbus surrounding the darkened Sun. The asteroid's atoms contribute to this ethereal glow, their Thomson scattering of photospheric light adding imperceptibly to the corona's luminous beauty. Coronal holes, regions where magnetic field lines extend into interplanetary space rather than looping back to the Sun's surface, appear as dark areas in the X-ray images of the corona. These holes serve as the source regions for high-speed solar wind streams that interact with Earth's magnetosphere to create geomagnetic storms and aurora displays. The asteroid's particles that enter coronal holes begin their journey toward the outer solar system, destined to become part of the tenuous medium that fills the space between worlds. The corona's magnetic topology changes continuously as the Sun rotates and its internal magnetic field evolves. Coronal loops brighten and fade, streamers shift position, and new active regions emerge as magnetic flux tubes rise from the solar interior. The asteroid's dispersed atoms serve as tracers for these magnetic changes, their emission signatures recording the dynamic evolution of coronal structures with each spectroscopic observation. Solar energetic particle events, accelerated by magnetic reconnection and shock waves in the corona, can reach energies exceeding those produced by the largest terrestrial particle accelerators. Some of the asteroid's heavier nuclei join these energetic populations, achieving velocities that represent significant fractions of the speed of light. These relativistic particles follow magnetic field lines that spiral outward from the Sun, creating radiation hazards for spacecraft and astronauts venturing beyond Earth's protective magnetosphere. The asteroid's complete ionization in the corona represents the final transformation of matter that began its journey as condensed grains in the early solar nebula, from solid rock to liquid magma to plasma to fully ionized nuclei. The material has experienced every possible state of matter. Only took 4.5 billion years to return home to the furnace that created it. The irony glows softly in X-ray wavelengths, invisible to human eyes but recorded faithfully by instruments designed to study the most extreme environments in the solar system. Coronal physics operates at the intersection of thermodynamics, electromagnetism, and fluid mechanics, creating a complex system where small-scale processes influence large-scale phenomena through nonlinear interactions. The asteroid's atoms become part of this system, their individual motions contributing to collective behaviors that emerge from the statistical mechanics of millions of charged particles interacting through electromagnetic forces across vast ranges of spatial and temporal scales. Below the corona, beneath the chromosphere and photosphere, the asteroid's ionized atoms sink into the convection zone, a vast spherical shell that extends from 70% of the Sun's radius outward to the visible surface. Here, in this realm of churning plasma cells, energy transport shifts from radiation to convection, and the asteroid's constituent particles begin a journey that will carry them through circular currents lasting hundreds of thousands of years. The convection zone operates like a cosmic heat engine, driven by the temperature difference between the nuclear furnace at the Sun's core and the relatively cool photosphere above. Granulation patterns visible on the Sun's surface represent the upper manifestation of convective cells that extend downward for 200,000 kilometers, a distance equivalent to traveling from Earth to the Moon and halfway back again. These cells, ranging in size from a few hundred to several thousand kilometers across, rise and fall in predictable cycles that transport energy upward from the Sun's interior. The asteroid's atoms become entrained in these massive circulation patterns, their upward and downward motions synchronized with plasma flows that dwarf any meteorological phenomenon on Earth. Temperature gradients in the convection zone follow the adiabatic lapse rate, meaning that rising plasma cools at a predictable rate determined by the expansion of gas under decreasing pressure. Descending plasma heats up as it encounters higher pressures in the Sun's depths. This thermodynamic cycle, repeated billions of times across millions of convective cells, creates the mechanical energy that drives mass transport throughout the outer third of the Sun's interior. The asteroid's atoms experience these temperature variations as they ride the convective currents, cycling between regions where temperatures exceed 2 million Kelvin and zones barely hot enough to maintain complete ionization. Plasma physics in the convection zone operates under conditions that challenge theoretical understanding. The Reynolds number, a dimensionless quantity that describes the ratio of inertial forces to viscous forces in fluid flow, reaches values exceeding 1014 in solar convection, making it the most turbulent environment known in the universe. For comparison, the most turbulent flows achievable in terrestrial laboratories reach Reynolds numbers of only 10 or 6. This extreme turbulence creates a cascade of energy, from large-scale convective motions down to microscopic plasma instabilities. The asteroid's heavier elements iron, silicon, magnesium become mixed throughout the convection zone through a process that operates like a cosmic blender. Convective mixing erases chemical gradients that might have existed in the Sun's outer layers, creating a well-stirred reservoir where element abundances remain uniform from the base of the convection zone to the photosphere. This mixing process explains why spectroscopic observations of the Sun's surface accurately reflect the composition of material in the convection zone's depths. Magnetic field generation occurs throughout the convection zone through a process called the magnetic dynamo. The differential rotation of the Sun, its equator, spins faster than its poles combined with convective motion, stretches and twists magnetic field lines into complex configurations. The asteroid's ionized atoms, being excellent electrical conductors, participate in this dynamo process by carrying electric currents that amplify and maintain the Sun's global magnetic field. These currents, though individually tiny, sum to create magnetic phenomena that influence the entire solar system. Convective turnover times vary with depth and latitude, creating a complex three-dimensional circulation pattern that astronomers are only beginning to understand through helioseismic observations. Near the surface, convective cells complete their circulation in minutes to hours, while deeper cells may require months or years to complete a full cycle. The deepest convective motions, driven by the steepest temperature gradients, operate on timescales approaching 1,000,000 years. The asteroid's atoms will participate in all these circulation patterns, their ultimate fate determined by which convective stream captures them during their descent. Sound waves generated by turbulent convection propagate throughout the Sun's interior, creating the acoustic oscillations that helioseismologists use to probe solar structure. These waves, with periods ranging from minutes to hours, reflect off the Sun's core and travel back to the surface, where they create measurable oscillations in brightness and velocity. The asteroid's dispersal briefly modifies the local density structure, creating subtle changes in the wave propagation that could, in principle, be detected by sufficiently sensitive instruments. The convection zone boundary, located at approximately 70% of the solar radius, marks a fundamental transition in the Sun's energy transport mechanism. Below this boundary, in the radiative zone, energy moves outward primarily through the emission and absorption of photons. Above it, convective currents dominate energy transport. The asteroid's atoms that sink to this boundary encounter a region where the physics of energy transfer shifts dramatically, like crossing from a flowing river into a still lake. Helium settling represents a slow but significant process in the convection zone's chemical evolution. Helium atoms, being more massive than hydrogen, tend to sink gravitationally through the convective medium over timescales of millions of years. This process gradually increases the helium abundance in the Sun's core while decreasing it in the convection zone. The asteroid's contribution of trace helium joins this slow gravitational sorting, its atoms destined to participate in the Sun's long-term compositional evolution. Convective overshoot, a phenomenon where convective motions penetrate slightly beyond the formal boundary of the convection zone, creates a transition layer where both convective and radiative energy transport operate simultaneously. Some of the asteroid's atoms may become trapped in this boundary region, their motion constrained by the changing physics of energy transport. This overshoot layer, only a few % of the solar radius thick, plays a crucial role in determining the Sun's overall structure and evolution. The asteroid's organic compounds, completely dissociated into their constituent atoms, contribute carbon, nitrogen, and oxygen to the convection zone's inventory of heavy elements. These elements, originally formed in the nuclear furnaces of massive stars and expelled in supernova explosions, have travelled through interstellar space for billions of years before condensing into the asteroid that now feeds them back to a stellar environment. The cosmic recycling continues, each atom destined for further adventures in stellar nucleosynthesis. Magneto-hydrodynamic instabilities in the convection zone create small-scale turbulence that operates on spatial scales ranging from kilometers to meters. These instabilities, driven by the interaction between magnetic fields and plasma flows, dissipate energy and contribute to the heating of the solar atmosphere above. The asteroid's conducting atoms participate in these microscopic processes, their collective motion contributing to electric currents that generate magnetic fields and electromagnetic heating. Pressure at the base of the convection zone reaches approximately 10 billion pascals, equivalent to the pressure found 1,000 kilometers beneath Earth's surface. Under these conditions, hydrogen exists in a partially degenerate state where quantum mechanical effects begin to influence the gas properties. The asteroid's hydrogen nuclei, stripped of their electrons in the corona above, experience this exotic matter state as they sink toward the Sun's radiative interior. Temperature stratification in the convection zone follows nearly adiabatic profiles, meaning that entropy remains approximately constant along convective streamlines. This thermodynamic constraint creates a specific relationship between temperature and pressure that determines the convection zone's vertical structure. The asteroid's atoms trace out these adiabatic curves as they rise and fall with the convective currents, their thermodynamic state evolving according to the fundamental laws that govern gas behavior in stellar interiors. The convection zone contains approximately 30% of the Sun's total mass, making it a substantial reservoir for the storage and transport of energy, angular momentum, and chemical elements. The asteroid's contribution to this reservoir remains infinitesimal, yet its atoms will participate in the zone's collective behavior for geological timescales. Some atoms may reach the surface within decades, while others might remain trapped in deep convective cells for hundreds of millennia before eventually rising to contribute their energy to the photosphere's radiant output. Convective energy transport efficiency in the Sun exceeds that of any terrestrial heat engine, achieving energy transfer rates that would require technological systems of impossible complexity to duplicate. The convection zone moves approximately 10 to 26 watts of power from the solar interior to the surface, enough energy to supply human civilization for billions of years. The asteroid's atoms become part of this cosmic power plant, their kinetic and thermal energy contributing to the vast flow of energy that sustains life throughout the solar system. Beneath the convection zone lies the radiative zone, a spherical shell extending from 30% of the Sun's radius outward to the convective boundary above. Here, the asteroid's atoms enter a realm where energy transport operates through an entirely different mechanism, the emission, absorption, and re-emission of photons in an intricate dance that can last hundreds of thousands of years. In this dense medium, where pressures exceed 1 billion Earth atmospheres and temperatures climb toward 15 million Kelvin, light itself becomes trapped in a random walk so complex that photons created at the zone's base take longer to reach the surface than human civilization has existed. The radiative zone's density increases dramatically with depth, rising from roughly 1/10 the density of water at its upper boundary to nearly 10 times water's density at its base near the solar core. Under these extreme conditions, matter exists in a state unknown anywhere else in the solar system, a fully ionized plasma so dense that quantum mechanical effects begin to influence the behavior of particles. The asteroid's atoms, now completely stripped of electrons, navigate this environment as bare nuclei surrounded by a sea of free electrons that move according to the statistical laws of degenerate matter. Photon diffusion in the radiative zone operates through a process that physicists describe as a drunkard's walk. Each photon travels only a few millimeters before encountering an electron or ion that absorbs it and immediately re-emits it in a random direction. This absorption and re-emission cycle repeats billions of times as each photon slowly works its way outward through the dense plasma. The asteroid's atoms participate in this process both as absorbers and emitters, their nuclei occasionally capturing photons and releasing them at slightly different energies, determined by quantum mechanical selection rules. Opacity. The measure of how effectively matter absorbs electromagnetic radiation varies throughout the radiative zone according to temperature, density, and composition. Heavier elements like the iron and silicon from the asteroid contribute disproportionately to the zone's opacity, despite their relatively low abundance. These elements possess numerous electron energy levels that can absorb photons across a wide range of wavelengths, making them particularly effective at trapping light. The asteroid's heavy element content, though infinitesimal compared to the zone's total mass, joins the Sun's existing inventory of opacity sources. Temperature gradients in the radiative zone follow a precise mathematical relationship determined by the balance between energy generation in the core and energy transport toward the surface. This gradient, steeper than the adiabatic lapse rate that governs convection, creates the thermodynamic conditions necessary for radiative energy transport to dominate over convective mixing. The asteroid's atoms experience these temperature variations as they diffuse slowly through the zone, their thermal energy increasing as they sink toward the hotter depths below. Magnetic fields in the radiative zone remain largely trapped and isolated from the dynamic magnetic phenomena occurring in the convection zone above, without convective motions to stretch and amplify field lines. Magnetic structures in the radiative zone evolve slowly, primarily through the process of magnetic diffusion. The asteroid's conducting atoms carry tiny electric currents that contribute to these fossil magnetic fields, preserving remnants of the Sun's primordial magnetic structure from the era of stellar formation. Nuclear burning occurs exclusively at the base of the radiative zone and in the core below, where temperatures exceed the threshold required for hydrogen fusion into helium. The asteroid's hydrogen nuclei that sink to these depths join the proton-proton chain reaction that powers the Sun's luminosity. These fusion reactions release gamma-ray photons with energies millions of times higher than visible light, beginning their long journey toward the surface through the radiative zone's labyrinthine path of absorption and re-emission. Hydrostatic equilibrium maintains the radiative zone's structural stability through the precise balance between gravitational compression and radiation pressure. Each layer of the zone supports the weight of all layers above it, through the pressure generated by trapped photons and thermal motion of particles. The asteroid's atoms contribute negligibly to this pressure balance, yet they experience its effects as they settle into gravitational equilibrium within the dense plasma medium. Helium accumulation in the radiative zone occurs gradually as the products of nuclear fusion diffuse outward from the core, unlike the convection zone above, where mixing homogenizes composition. The radiative zone preserves compositional gradients that reflect the history of nuclear burning and element transport. The asteroid's helium content merges with these existing gradients, its atoms destined to participate in the slow evolution of the Sun's internal structure over billion-year timescales. The zone's thermal structure exhibits remarkable stability, with temperature profiles that have remained essentially unchanged for billions of years. This thermal equilibrium results from the fundamental physics of radiative energy transport, which automatically adjusts to maintain the precise temperature gradient required for steady energy flow. The asteroid's brief thermal perturbation dissipates quickly into the zone's vast thermal reservoir, leaving no lasting signature in the Sun's internal temperature distribution. Quantum mechanics becomes increasingly important in the radiative zone's deeper regions, where electron degeneracy pressure contributes significantly to the total pressure support. Under these conditions, electrons behave according to Fermi-Dirac statistics rather than classical Maxwell-Boltzmann distributions. The asteroid's electrons, stripped away in the corona above, join this quantum mechanical electron gas that fills the spaces between nuclei throughout the radiative zone. Neutrino production in the nuclear reactions at the zone's base creates a constant flux of nearly massless particles that escape the Sun immediately, carrying away a small fraction of the nuclear energy without interacting with the dense plasma. Unlike photons, which require hundreds of thousands of years to diffuse outward, neutrinos travel at the speed of light and reach Earth's surface just 8 minutes after their creation in the solar core. The asteroid's hydrogen nuclei that undergo fusion contribute to this neutrino flux, their nuclear reactions adding to the stream of particles that pass through Earth every second. Chemical diffusion operates slowly in the radiative zone, gradually separating elements according to their mass and ionization state. Heavier elements tend to settle gravitationally while lighter elements diffuse upward, creating subtle composition gradients that evolve over stellar lifetimes. The asteroid's diverse elemental inventory from lithium to iron participates in this cosmic sorting process, each element finding its equilibrium distribution within the zone's gravitational and thermal environment. Pressure ionization maintains the complete dissociation of all atoms throughout the radiative zone, despite temperatures that would allow partial recombination under lower pressure conditions. The extreme pressure compresses electron orbitals to the point where bound states become energetically unfavorable, ensuring that all matter exists as a plasma of free nuclei and electrons. The asteroid's atoms remain completely ionized throughout their residence in this zone, their electronic structure reduced to bare nuclear charges. Convective instability boundaries mark the transitions where the temperature gradient becomes steep enough to trigger convective overturning. The asteroid's atoms that approach these boundaries may become entrained in small-scale convective cells that transport them rapidly upward or downward, dramatically altering their journey through the solar interior. These boundary layers, though thin compared to the radiative zone's total thickness, play crucial roles in determining the overall structure of the Sun's interior. Radiative acceleration affects different elements unequally, with the radiation pressure on heavier elements sometimes exceeding gravitational forces. This phenomenon can drive selective mass loss and element separation in stellar atmospheres, though in the Sun's case, the effects remain subtle. The asteroid's iron and silicon nuclei experience slightly different radiative forces than hydrogen and helium, contributing to microscopic element separation processes that operate over million-year timescales. The radiative zone serves as the Sun's primary energy storage reservoir, containing thermal energy equivalent to the star's total luminous output for several million years. The asteroid's atoms become part of this energy bank, their thermal and kinetic energy contributing to the reservoir that buffers the Sun's output against variations in nuclear energy generation. This thermal inertia explains why the Sun's luminosity remains remarkably stable, despite the chaotic nature of nuclear fusion reactions in the core below. Stellar evolution models predict that the radiative zone will gradually shrink as the Sun ages, and its core accumulates helium ash from hydrogen burning. Over the next several billion years, the convection zone above will deepen as the Sun evolves toward its red giant phase. The asteroid's atoms will experience this slow evolution, their environment changing imperceptibly as the Sun's internal structure adjusts to the long-term consequences of nuclear energy generation. At the base of the radiative zone, where temperatures exceed 15 million Kelvin and pressures reach 100 billion Earth atmospheres, the asteroid's hydrogen nuclei encounter the nuclear furnace that powers the Sun. Here, in the core region, extending from the center to approximately 25% of the solar radius, the fundamental forces of nature overcome the electromagnetic repulsion